Kaoutar is a principal research staff member at the IBM T.J. Watson Research Center. She leads the IBM's AI Hardware Center's test beds. So, looking at for the IBM perspective, how to automate doing a lot of this testing and integration. And I think her talk will delve into this and I think go into a number of interesting areas. She got her PhD from Rensselaer Polytechnic Institute, RPI, and I think got a Best Thesis Award for that. She got her master's degree from Al Aqwan University in Morocco, which is in the middle of the Atlas Mountains. I think for many in the West anyway, the Atlas Mountains are not necessarily well known, but that they're very beautiful and a very interesting area to go if you ever get the chance. So with that, I will turn it over to you, Kaoutar. Welcome, and we look forward to your talk.
Thank you, Eric, for the introduction. Let me share my screen. Can you see my slides?
I see the FastPath online schedule.
Oh. Let me try one more time. What about now?
Yes, now we see it. And maybe if you go into screen show mode there, that looks good. Thank you.
Thank you. Thank you so much, Eric. It's a pleasure to be here. My name is Kaoutar El Maghroui, and my initial background from my PhD days is we're in distributed systems and high performance computing. Now, after several years at IBM Research, my current systems are inefficient deep learning techniques with a focus on AI automation across the life cycle for AI applications. As Eric mentioned, I'm part of the IBM Research AI Hardware Center, leading our testbed infrastructures and efforts and working closely with our partners. And in this talk, I would like to give a brief overview of some of the research directions we are pursuing in the AI Hardware Center, especially with regards to efficient deep learning, and then give an overview of some of the state-of-the-art in hardware-aware neural architecture search based on a recent survey that we did. So, deep learning has achieved incredible performance in numerous fields, including computer vision, speech recognition, NLP, and so on. However, most of these models are very expensive and computationally expensive to run. Computation, especially devices like mobile phones or embedded devices. And as the figure on the left shows, DNN models are getting larger and deeper with millions or even billions of parameters. And that translates into high computational demands. In fact, compute requirements for large AI training jobs have been doubling every 3.5 months. And if you look at the computer requirements to train AI models over the last 5 to 6 years of some of these flagship demonstrations that we've seen in the popular press, this, trend is going, and we used to be really impressed with Moore's law, but this thing is really doubling every, 3.5, months, which is really huge. What are the implications of this when it comes to, deployments? So this, comes with huge increase in computational costs, as I mentioned, but also increased carbon footprints. So some recent study from the University of Massachusetts at Amherst, they released a startling report, estimating that the amount of power required to train and search a certain neural architecture involves the emission of roughly, 626,000 pounds of carbon dioxide, which is equivalent to what, a car, 5 cars would emit in their lifetimes. If we keep going at this rate, we're going to consume the entire energy, budget of the world, just, training these models. So all of this, especially as the future of AI is moving to the edge, and AI becomes increasingly more important at the edge, we really need to consider more seriously a shift from state-of-the-art model accuracy to state-of-the-art efficiency. And it is expected that learning at the edge, especially with reinforcement learning, is going to play a key role in the future. Edge intelligence, also comes with various challenges such as resource-constrained devices, CPU, memory, power, etc. The difficulty of deploying models on a fleet of devices, and also the instability of the network connectivity, and which is often, not guaranteed. And also the fact, that data cannot leave the device in many of the cases for privacy and security concerns, for instance, in the domain of healthcare, for example. And if we look, more closely at inference at the edge, energy efficiency becomes very important. Deep learning applications in small edge, especially, must meet a number of constraints: low latency, low power consumptions, within the cost constraints of these small devices. And this, again, motivates optimized architectures, microarchitectures, and also optimized precision. And, this is an example that shows, as we're moving from IoT to mobile to automotive, the varying requirements that we have in terms of low voltage operations that are needed for optimal energy efficiency. And here, looking just at accuracy is not enough. Metrics like tops per watts or even tops per area become very important. So looking, at the AI hardware trends here, so it's still really inefficient. Broadly, it's inefficient the way we train deep learning networks with existing hardware, which are mostly dominated by GPU architectures. And this gives rise to this tremendous growth in specialized AI hardware accelerators that are purpose-built to deploy deep learning applications efficiently, especially in real-time systems and edge devices. And here we see some of the trends that we're observing. So it's really pretty clear that AI is the next big thing that is scaling up and driving the semiconductor industry. And we see the trends here. That there is AI ASICs are expected to have the biggest growth in the future, but also an important observation here that the optimal compute architectures for AI will vary by application and use cases and hardware deployment scenarios. So the figure on the right shows different application domains like in automotive or mobile and so on, and where GPUs will be needed, ASICs will be needed, and so on. So, and I'd like here to quote Phil Blanson from the Department of Computer Science at Oxford and DeepMind, who said that developing deep learning models is a bit like being a software developer 40 years ago. You have to worry about the hardware, and the hardware is changing quite quickly. Being at the forefront of deep learning also involves being at the forefront of hardware, what hardware can do. So in this grand landscape of building efficient neural networks, we really see three approaches come into play. The first one is increasing model efficiency through designing accurate and efficient neural networks. The second one is increasing hardware efficiency, and this is through purpose-built AI hardware. And the third one is increasing design efficiency by automating the design of efficient neural architectures through neural architecture search. And this is especially going to be very important to democratize, AI design and efficient AI across many domains and applications. So let's look at the first one, the model efficiency. Here, I'm just going to kind of give a quick overview. What are the key techniques that are standing out? So some of the techniques that have been, widely used, things like pruning, compact convolutions, quantization, reduced precision, and knowledge distillation. So pruning has the goal of optimizing the model by eliminating the values and the weights, of the tensors. And the aim here is to get computationally cost-effective models that take less amount of time in training. So it's a way to reduce the size of the neural network through compression. And after the network is pre-trained, then it is fine-tuned to determine the importance of the connections. With regards to compact convolutions here, the goal here is to reduce the number of channels or kernel sizes. And a lot of these techniques, there are also some best practices, especially around designing these neural networks on constrained devices like mobile. So we've seen the emergence of architectures like mobile net, efficient net, and a lot of the techniques they relied on is, really downsizing the the number of channels and kernel sizes, for example, replacing 3x3 filters with 1x1 filters, and also optimizing the downsampling. And reduced precision here, the fundamental idea here is that we convert the weights and input into integer types, and this helps us consume less memory with regards to the MAC operations in hardware, and also allows also for speed up. The last technique here is knowledge distillation, which refers to the idea of having compressing the model by having a bigger model teach a smaller model, and so in a step-by-step process. And what is being done here is the bigger model kind of uses these soft labels to guide the students. So the smaller network is then trained to learn the exact behavior of the bigger network by trying to replicate its output at every level. So the next thing here that's really becoming important is the hardware efficiency. And this is a huge area of investment and focus at IBM Research, where we're trying to imagine the future of AI hardware computers and accelerators and realize it beyond, the world of GPUs. So GPUs are the best examples of what we have today, but by no means are the ideal architectures to implement some of these AI architectures, especially at the edge. So to address this, in February 7 of 2019, IBM launches this research collaboration center to drive next generation AI hardware. And so the AI Hardware Center was kicked off, and IBM Research made a commitment to invest $2 billion with New York State also as well over the next 5 years. This generated a lot of interest in the technical community, and this also shows that this is a serious endeavor for IBM Research and the IBM company to build an ecosystem of enterprise and academic partners to drive next generation AI hardware accelerators. So what we're doing here at the AI Center, it's really across the stack approach, looking at hardware, algorithms, and software. And at the level of the software, our worldwide team is looking at compiler optimizations, feedback to hardware design, simulation and emulation of future hardware. At the algorithmic level, we're exploiting reduced precision scaling, other techniques like sparsity, quantization, aware scaling, training, model compression, auto AI. And at the hardware level, we're really looking at designing chips that exploit some of these algorithmic advances, but also going beyond digital computing, looking at analog AI, where we're exploiting in-memory compute advances. So here, this shows the roadmap that we have in the AI Center, that IBM Research have, of what's beyond the GPU. So we have plotted here some existing and projected performance metrics of mostly GPU hardware that exists in the market today or has been announced by major players. You see here, there is been this steady progress that at a rate of 2.5x per year over the last few years. So the question here, what really technology innovations are needed to develop to be able to continue this trend beyond the GPU? So here, to extend the performance through the 2025, we rely on these two key things: the approximate computing principles, where we're building digital AI cores with reduced precision, and as well as analog AI cores, which could potentially offer an additional 100x speed up, especially with energy efficiency. So with regards to reduced precision scaling, the key things here we're doing, IBM Research has been leading in reduced precision scaling with the focus of also maintaining ISO accuracy. And 5 years ago, around 5 years ago or 6 years ago in 2015, our team proposed the first reduced precision DNN training and started this precision scaling journey. And then we've shown that precision scaling has been very effective for hardware performance improvement in these years. And also it improves energy efficiency quadratically. And you see here the progression, over the years with additional demonstrations, with 8 bits training that were shown in NeurIPS 2018 and 2019. And more recently, in 2020 with the first demonstration of 4 bits training. We also have shown, the highly accurate 2-bit and 4-bit inference at SysML 2019. And very recently, we introduced, the AI chip that's leading in precision scaling, which was highlighted in the ISSCC 2021 conference. So the next step in this evolution is of specialized hardware for AI is rooted in addressing the performance efficiency loss from data movements, because that's really at the core of driving more energy consumptions and more compute is the data movement that happens in AI applications. So, and the way to address this is through analog NVM in memory, which eliminates the Van Neumann bottleneck and allows performing computations directly in memory. So the approach here is analog accelerators avoid the Van Neumann bottleneck by performing computations in place. And the analog approach uses arrays of non-volatile memory or programmable, what we call resistive processing units, RPUs, that encode the neural network weights. So computations like vector matrix multiplications, MAX, or element-wise matrix updates can be done in parallel and in constant time with no movement of the weights. So, so this, basically covers, all aspects, of the matrix multiplication or element-wise matrix update in constant time, thus covering all aspects of DNN training, forward propagation, backward error updates, and weight updates. And just, very recently, we have open sourced the IBM Analog Hardware Acceleration Kits with the goal of building and supporting an open community, an ecosystem that's interested in understanding and also contributing to the capability of in-memory computing devices in the context of artificial intelligence. So this is available online, and I hope you get to explore it. So this is an open source PyTorch based toolkit that simulates analog Mac operations, including analog backward updates, and also it simulates a wide range of analog AI devices and crossbar configurations, things like PCM, RAM, and so on. And it also abstracts, allows, also adding new abstract devices. So we invite the community, to leverage this tool and also contribute to it with the purpose of understanding the future of AI acceleration through analog. And as part of, of our roadmap of evolving features, we're soon going to launch a cloud experience, which is, think of it as a no-code, it's a composer that allows end users to play with the toolkit in a visual way and then select various configurations, devices, and then do also hardware-aware training with analog. This is going to be released very soon, I think in the next month. So moving forward here, I want to talk more now on the design efficiency, and which brings us to the automation or the auto AI principles here. And so this is, a very emerging and important approach for building efficient neural networks, and especially now that hardware-aware neural architecture search is going to be key towards democratizing AI. So today's neural networks are extremely complex and they're growing fast, in complexity and model size. And we all know that handcrafting, these neural networks is a very expensive and time-consuming and ad hoc process. Some of these, flagship demonstrations, for example, Google Nets and so on, they have, they're deep. They also, have some architectures that's really, hard, to for, a typical average data scientist to think of. It requires many years of expertise and also intuition and understanding of the statistical nature of these algorithms, the math behind them, and so on. And moving also to the edge intelligence, understanding also the efficiency of these neural networks and designing them with efficiency in mind, requires also building into this design hardware characteristics, and which is really very hard for non-hardware experts. And I think the previous talk really nicely laid down, some of these challenges of building these T-shapes, especially in the area of AI. It requires kind of a team effort where designers, software engineers, hardware experts, and so on need to work together and to be able to really to build efficient and performing neural networks that you can deploy in production. So some of the key questions we're trying to address, in the survey that we did recently, this is available in archive and, was submitted to IEEE proceedings. So this was a comprehensive survey that we did, and this also is a joint collaboration with the University Polytechnique Hauts-de-France. And so some of the key questions we try to address here: what are the key algorithmic components of hardware NAS, and how does it compare with general NAS? And also, what search spaces are more friendlier to hardware NAS, aware NAS? And what are some of the existing challenges and future directions? Have we really solved this problem or not yet? So if you look at NAS and hardware NAS in particular, so hardware NAS is a subfield of NAS, which is a subfield of hyperparameter optimization, which is also a subfield of the general field of automated machine learning, which looks not just at, figuring out or the right architecture or the hyperparameter, but also doing automation across the entire ML lifecycle, including data pre-processing, including model deployment, including getting feedback, as the model is being deployed, and so on. And looking at the trends, this is a very highly trending topic. NAS has been trending in the past few years, and this shows the number of papers that has been published in the space, all NAS papers in blue here on the right. And in particular, hardware-aware neural architecture search has recently gained tremendous attention with the focus on automating the design of neural networks deployed in resource-constrained devices. You can see here also that the number of papers is increasing rapidly. And these were stats, collected as of December 2020. I'm sure there are even many more papers now in the space. If we look also at, these hardware NAS, what hardware platforms they're targeting, and also what types of neural network architectures they're targeting. You see here on the left that it's mostly, still GPU centric, but we see also a rise in interest in environments like FPGAs and also, ASICs. So they're also, kind of getting more momentum as the community is exploring those new hardware accelerators. And in terms of the type of networks considered, this is also still vision dominated. If you see here in 2020, most of the networks considered were types of extended convolutional neural networks, and standards, also CNNs, and a little bit, of focus on RNNs and transformers, especially with the surge of transformer-based networks. We see the community started paying attention, especially in the NAS space, but it's still a much smaller subset, and it's challenging, to do NAS for transformers. So this slide just shows, general NAS components. So you need to have an architect, you design an architecture space, and then design a search algorithm and the evaluation strategy. And then basically, once you, from the architecture space, you have to pick an architecture and then search, what's the best architecture and get the feedback based on the evaluation strategy. And you do this iteratively until you find the best model that maximizes, the accuracy. And general NAS, has been done, this is still a very evolving space with a lot of research in the space here, a lot of publications. And, I feel also the NAS itself, it still hasn't kind of converged into, the best strategies and so on. So there's a myriad of strategies here being used with regard to the search space, the search strategy, and the evaluation. And if we want to kind of understand how does hardware NAS compare to this? So this becomes a bit more complex here. So the search space would include hardware, search space in certain cases. The search algorithm, they are still, here using the regular search algorithm that are used in general NAS. And the evaluation strategy here, we see that the hardware cost measurements start, to play here and being taken into consideration in the search algorithm because we need to incorporate, these design efficiencies into the search. And there are some, strategies where, they search for the best architecture and then they try to specialize it on target hardware, or even try some additional optimizations like transferring the model, applying quantization, pruning, and so on. In terms of the search space, this is also lots of different techniques here. There is, in the architecture search space, there are different approaches here, things like layer-wise search space, where you select for each layer an operation among a predefined set of operations, a cell-based search space, where you have kind of fixed cell structure, and then you need to find the operations in a block and repeat the block. So the idea here is you need to search for the best cell structure, and then you take those cells and stack them to construct the final neural network. And there are others, these are the most popular one, layer-wise and cell-based, but there are others like hierarchical search space, where you select operations in a block and then figure out the order of the blocks, and then the hyperparameter search space, where you fix a macro architecture and select its architecture hyperparameters. So the added thing here in hardware NAS is sometimes, the hardware characteristics are also, are augmenting the overall search space for NAS. And here there are two approaches that we see: template-based, where you select a set of predefined templates. For example, an ASIC selects from a set of ASIC templates, or parameter-based, where you select also different parameter configurations. For example, in FPGA, you select the tiling parameters, or you select the number of processing elements, or the register file size, and so on. And in terms of, the search formulation, at the core of this is basically similar to NAS. You have an objective function that you need to optimize. So here you want to maximize, the accuracy. But what we see here is it's a constrained optimization problem. And one approach, that was used to incorporate the hardware feedback is to add a term for latency. So if you see the equation here, the latency of the model with some threshold here, and with some learnable parameters to control the effect of the hardware constraints on the global objective function. So in the grand landscape, of all these different optimizations, there are different ways, of defining the objective that you would like to optimize. So there are single objective optimizations or multiple objective optimizations, and often, when you formulate the problem, single objective, multi-objective, it adds, to the complexity of the search, and sometimes it becomes intractable. So there are techniques to relax this, so you can solve this. And sometimes, two-stage methods are used. You first find the best architecture, and then you apply, efficiency techniques like compressing it, or you do a constraint optimization where you consider the hardware cost as a constraint in the optimization problem. But here, sometimes what you have to do is you have to turn this, if you're using differentiable techniques, you have to turn the hardware cost into differentiable terms. So you can also use standard, gradient-based methods to solve this. Multi-objective functions, this is less used in general that we see, but once they're used, they usually rely on scalarization methods where they try to turn, the objective functions into, multiple objective terms, things like accuracy, memory, and energy, and then you do these additive terms to be able to solve it. Or they're using evolutionary algorithms like the elitist evolutionary algorithm, where you also, they have used multiple objective functions. So this is an example of Proxylus Nas from MIT, which uses a loss function that comprises the, both the cross entropy and the hardware wear constraints. And you can see here that the way they've done this is basically they use this in their reinforcement learning agents. So they do a combination of both gradients, differentiable technique, but also reinforced algorithm. And they have added, this latency term, and a policy is learned to decide, whether to add, remove, or keep a layer, as well as whether to alter, the number of filters. And they also, basically made the latency differentiable by introducing this latency regularization term. So what we've seen is, differentiable neural architecture search is one of the, famous speed up techniques that have been used in NAS, which relies on weight sharing and one-shot models. Especially that earlier reinforcement learning techniques, they have required really many computational resources, thousands of GPU days for reinforcement learning, or even for evolutionary techniques, which is really not feasible. And the idea of differentiable neural architecture search, came to address this, which made the search phase very efficient. And the way they've done this is by relax, the discrete optimization problem into a continuous problem. So a very clever idea that was used to, increase the efficiency of the search space by also kind of learning together the weights and then the architectural parameters doing these continuous relaxation. So with regards to looking at, constructing a neural network that targets multiple devices, there are different challenges here. And especially, due to the unique design of each hardware, and their specialties, are usually different, which may yield different directions for optimizations. So what we have observed is different devices have different design choices. Different devices can also favor very different network structures under the same hardware cost metrics. And these are some of the studies that were done. This figure shows per layer profiling of mobile net v3, the figure on the bottom. And comparing two architectures, CPU and Qualcomm hexagon architecture, and you see here that the total, the latency varies. This is on the same number of layers, and and it also varies from the beginning to the end. And on this figure here, you see that the correlations coefficients between real or estimated hardware cost between different devices is very small. So the same layers, the same operations can behave very differently from one hardware to the other. And this just shows that you cannot build one neural network that's optimized for one device and then expect it to run efficiently on another device. So hardware specialization is really key. And this makes this problem in general difficult. So many speed up techniques are used, to kind of speed up the search for hardware NAS, things like early stopping, using proxy datasets, or the differentiable techniques like weight sharing or super networks, where you train a very super network with all possible architecture paths, and then you sample from that super network to specialize it on a particular targets, or some accuracy predictors, or even hardware cost measurements predictors also are being used, so that you don't have to train the sampled networks, but you just use an accuracy prediction to figure out what's the performance. In terms of hardware cost evaluation techniques, lots of different techniques are being used, things like real-time measurements, where you basically run directly on the hardware, or using things like a lookup table that is created beforehand and filled with the latency of each operation on the target hardware design. And this takes some assumptions, like assuming that these hardware operations are kind of independent when they're running on the device, which is typically not true in real time, but they try to provide a good approximation in general. And then other estimators or ways like low fidelity estimators or prediction models, where you build an ML model to predict the costs using architectures and dataset features. Some of the key challenges here, there is really a combinatorial explosion of the search space, if considering hardware metrics or efficient strategies like quantization and pruning. Also, the search strategy becomes very complex once you incorporate hardware feedback. In terms of benchmarking and reproducibility, up to this year, there has been no really hardware NAS benchmarks. There are like a set of good benchmarks for NAS in general, but until very recently, we've seen hardware NAS bench, which is the first hardware-aware benchmark that's published at ICLR 2021. And also the challenge of transferability of the AI models. Once you build on one architecture, it's really hard to transfer to others. To other hardware, and most of these NAS approaches are limited, to computer vision applications, and still a lot of work is needed, to generalize them across other domains. So just trying to summarize here some of the key takeaways. Hardware NAS, overall is a hard problem and still not a fully solved one. And we feel that there is still no principled approaches exist. So the key techniques that stand out in terms of the exploration that we've done, layer-wise search spaces seem to be more hardware-friendly than cell-based search spaces. Layer-wise search spaces, for example, are used in the Facebook FBNet approach. Using differentiable techniques and weight sharing become very important here as a way to speed up. And they also have shown a lot of promise in the area, not just in hardware NAS, but also in NAS in general. And also there is increasingly a lot of use of predictors, constructing these models to predict either training performance or to predict the hardware cost measurements. And also that's what motivated the hardware NAS benchmark, where they create this big benchmark where you can get where you can query the benchmark to get the hardware cost for a variety of architectures. There's also an emerging research in the basically joint optimization, including quantized aware and pruning aware predictors. So I'd like to wrap up, with this slide here that just, shows that, efficient deep learning methods, they're inevitable, they're really highly needed, but still it's an evolving landscape, and it varies across, lots of different techniques, whether, techniques that are trying to do model compression, or, hardware aware NAS techniques that are evolving with different ways to address the search space or the search strategy or the evaluation, or how we incorporate the hardware metrics into the search, or at the other techniques that are non-hardware agnostic, things, for example, that are really done at the hardware and the system level in terms of code transformations, things like loop tiling, loop unrolling, and so on. So I'll pause here and thank you for your attention, and happy to take any questions.
Hi, Kaoutar. Thank you for a really interesting talk and really laying out this important landscape and all the challenges in it. Unfortunately, we're slightly behind time at this point, although we are going into a break. So maybe we should take questions offline, or there are a couple in the chat if there was maybe one of those that you wanted to take, or barring that, like I said, maybe just request
Sure.
that people ping you offline.
Sorry, I didn't realize I took more time.
No, I think you also, we had you start late. So here, well, Parijat asked, is hardware NAS more like constrained NAS? So typical NAS algorithms can be used for hardware NAS by adding compute memory and other constraints specific to the hardware?
Yes, I think you can do it like that. So it is kind of constrained optimization here, where you have to add additional, you want to optimize for, model accuracy, but at the same time, you want to minimize, for example, the latency, or, there could be other metrics, things like memory consumption, the model size, the latency on the hardware. So I think you said it right, it's a constrained NAS.
Okay, so I put one in about IDM and its importance for analog, but again, in the interest of time, maybe I can certainly ping you offline. And again, I really appreciate the very interesting talk. So thank you.
Thank you.
And with that, we complete session one. We'll resume in about 50 minutes or so, which will be 1:45 Eastern time in the US, 17:45 UTC, and 10:45 a.m. on the US West Coast, and other time zones as appropriate. So thank you all for joining, and we'll see you all again in about a little less than 50 minutes at this point. Thank you.